So let me start today by introducing some toy model equation defined on the real line, and it's called the de Gregorio model. I think the model was introduced in 90. Anna, is he Italian, by the way? Do you know him personally? Oh, okay. So I never met him, but here is the model. Now omega is a function depending on time and space. And now the space is just the real line. And for some reason, I will assume that the integral in space of omega is 0. And here is the equation. Partial t omega plus u dx omega. So this is transport equals omega dxu. So this looks like the vorticity equation in 3D. And u, by definition, is given by the Zygmund inverse operator applied to omega. And you can forget about this for now. I will need that assumption later. So here, the key point is that in the right-hand side, we have omega times derivative of u. And derivative of u, that's the key point. Derivative of u is derivative of this Zygmund inverse, which is called the Hilbert transform of omega. So this model has several parallel properties with the 3D vorticity equation. For example, we have the Cauchy formula for de Gregorio equation. So what do I mean? Let x be the flow. If capital X is the flow of u, assuming that u is nice enough to have a flow, capital X, then the solution can be written in terms of the flow, just like the 3D vorticity equation. So omega t x dx is omega 0 at little x multiplied by the gradient of capital X at t comma x. Okay. So in particular, you can write de Gregorio equation in Lagrangian formulation. Okay. So this is just a formal model. There's some story behind it. Mainly, a few years before this model, there was even simpler toy model, which is just that time derivative of omega is omega times the Hilbert transform of omega. And that model was introduced by Konstantin Laks and Maeda as an extremely simplified model of the three-dimensional vorticity equation. I will talk a little bit about that model soon. Okay? So the claim is that in terms of existence and uniqueness of solutions, in Felder spaces, the theory is completely parallel with the 3D vorticity equation. So let me just state it as a theorem, but it's really parallel and just simpler than the 3D Euler case. So, okay, let k greater than 0 integer and alpha between 0 and 1. Okay. And assume omega 0, the initial data, belongs to ck alpha and also L1 in R. Okay. So this condition is not necessary. I will need it only later when we do the self-similar analysis. Okay, then there exists time and a unique solution, omega t of x, which belongs to the same space. ck alpha, let me just say like this for simplicity. Okay. And we also have the so-called Mill-Kato-Maeda criterion, which is exactly the same. The solution cannot be continued past some t star if and only if. Okay. So again, the question is, assume that there exists some t star such that for any times strictly smaller than t star, we have a unique solution in ck alpha. Okay. And the question is, can we define the solution after t star? And this is possible. So this is not possible if and only if this integral omega t. So this is slightly more precise version than I wrote last time, is infinity. And this is equivalent to this at infinity going to infinity as time approaches its. Okay, any questions? I think so. I think so. So it's known for 3D Euler, right? Yes. I think so, but I have not thought about it. Yes. So this at infinity can be slightly weakened to BMO. Okay, so this will be an exercise for you if you are interested. And I want to use this model to prove the properties of the Hilbert transform, which are needed to prove this theorem. And my claim is that the proof that I will show you for the Hilbert transform can be repeated for the 3D Euler equations. So the first inequality we need is just C alpha boundedness of the Hilbert transform. Strictly speaking, I need to do at infinity boundedness first. Strictly speaking, that is necessary for C alpha boundedness. But let me just do it first. Okay. So what's the claim? The claim is that for any alpha strictly between 0 and 1, we have Hilbert of F in the homogeneous C alpha in R, bounded by some constant depending on alpha. We can see the constant from the proof times F in C homogeneous alpha. Okay. So what is the Hilbert transform? Again, Hilbert transform by definition at X is so-called principal value integral of 1 over pi x minus y fy dy. And assume that F belongs to C alpha. So the goal is very simple. The goal, take 2 points, x and x prime, in the real line, and we want to show that HF x minus HF x prime is divided by x minus x prime to power alpha is bounded. In other words, this is bounded by some constant times x minus x prime to power alpha. Okay. So before we do this, there is an observation to do, which is that we can insert f of x here. So the claim is that the Hilbert transform at x can be rewritten. It's again principal value integral as 1 over x minus y multiplied by fy minus fx dx. So of course, strictly speaking, we have to add again 1 over pi 1 over x minus y fx dy. And this does not depend on y, so we can maybe pull it out. And the claim is that this integral is 0. And it's wrong because it's not integrable both near x and near infinity. Okay. So the correct thing is to do principal value integration, not just at singularity, which is at x, but also at infinity. This is very important, actually. So not only at x, but also at infinity. And y is less than 1 over epsilon. Okay. Or x minus y is less than 1 over epsilon. that should be. Okay. What's the point? If you now put this, then the quantity that you need to add again is the same integral down here, and that is 0. Because it's odd function, it's exactly 0 for each epsilon. So we can take epsilon going to 0. Okay. So from now on, principal value integral should be interpreted as this sense, and this is 0. And we have to do this because we want to use that f is Felder continuous. So in the integral, we need a difference of f in two different points. So now we can start the estimate. Okay? And again, this is annoying to write every time. So I erase and just write TV. Okay. So what do? We split this integral into two regions. Okay? So in the real line, there are these 2 points, x, x prime. This real line is parameterized by y. And in the first step, we consider, say, the interval like this, which is interval centered at x and radius 2 times the difference or the distance. Okay. So in this region, okay, we just integrate it directly. Okay, so what we do here, we split the integral into two regions. The first region is the set of y such that y minus x is less than 2 times x minus x prime, and the remaining. Okay. So in this region, in this integral, we are going to take advantage of the fact that this interval is small. Okay. So let me call this maybe I. Okay. Then absolute value of I is bounded by integral in this small interval, and you just take absolute values inside the integral. Okay, so this is easy, dy. And we use the only information that we have, which is that f is C alpha. Okay? So bounded by C alpha, homogeneous C alpha, times, here we get x minus y to power alpha divided by power 1, x minus y, alpha minus 1 dy. And x minus y is from 0 to 2 times x minus x prime. So you calculate this integral. You get some constant depending on alpha from this integral times x minus x prime to power exactly alpha because it's alpha minus 1, and then you integrate. This is integrable if alpha is positive, and you get exactly this times the norm. Okay. So now we are left with this huge region here and there. There, we are going to subtract the corresponding integral for the Hilbert transform at x prime. Okay? Because we are estimating the difference, but the point in this local region is that we do not even need to use that we are taking a difference. We've just bound the individuals. And that's what we are going to do with this term as well. Okay? So Hilbert transform at x prime is just same expression. X prime minus y. And we again need to introduce this guy. Okay? What do we do? It's important that even for this integral, we split y into the same region, here and outside. Okay? Here is a slightly tricky point. Okay? When we were estimating this integral, this interval was centered at x. So maybe when you do it there, you want to do it in an interval centered here, but it is better to split y integral into the same region, okay? This region. Estimate this integral here, which gives the same estimate with slightly different constant. And what's the purpose of doing this? Because then we have the same integral in y, which we can just combine. So let's call this region J, okay. So the claim is that we now only need to estimate the principal value, 1 over pi, integral in J. Okay, J is that and also here. Just the difference of these two. And dy. Okay. And here comes another trick. We want to replace this by x prime. Okay. We want to replace this by x prime. And then there will be, because we have replaced this by f at x prime, there is another term which involves f of x prime minus f of x integrated against the singular kernel, okay? And this can be estimated directly, okay, to be of this form after cancellations. Okay? So I leave it as an exercise, okay? I replace this by f of x prime. Yes?
I is the first term. Then integral you have achieved I, capital I.
Yes.
Limited I. What about the second term? Y minus x strictly greater than 2x. Modulus of x minus x.
So that's J, right? Yeah, that's J. Okay, maybe it was not clear enough. So we have this integral. We split the y region into I and J, which is just the complement. Okay. We split this integral by the exact same regions, I and J. Okay. So this integral estimated in I, you just prove the exact same bound. Okay? Because here, what only matters is how far is y from your singularity. And that is of order of the distance of 2 points. So we have integral in J remaining, which we combine. And another trick is to replace this x by x prime. Then you need to add another term, but that term is just f of x prime minus f of x, which goes outside. And then you have this singularity integral, which is canceled by odd symmetry. So what's the whole point? Now they are equal, and we can combine. So in this huge region, you cannot close an estimate unless you write it as a product of differences. You need to gain decay from basically extra decay of the derivative of the kernel. And you have to use again the Hölder continuity of our function. So once you arrive at this expression, now you can take absolute values and estimate. Why? This is after taking the absolute value bounded by the difference x minus x prime. And it's a small exercise that you can bound it by x prime minus y squared. Okay. So if you just combine the fractions, you have this times that. But in this interval J, this is very close to that. That's why you get this estimate. And this in absolute value, of course, is bounded by this to power alpha times the semi-norm. Now what's the point? The point is that J is contained in the region, J is contained in the region where x prime minus y is greater than x minus x prime. Because that region is this. This is larger than J, but it's okay. We are just estimating in a larger region. Now what's the point? We have this vector with power alpha minus 2, which is integrable in the large region. And what's the integral? Integral is just what we need, alpha minus 1. And there is this 1 power. So if you do this integral correctly, then you just get that this is exactly some constant, again, depending on alpha, x minus x prime, power alpha, f, homogeneous C alpha. Okay, now this is exactly this. Okay, so that's the end of the proof. Any questions? Yes? Yes, this estimate holds with just homogeneous norms. Yes. But then, of course, there is this technical issue whether the Hilbert transform is well defined in this space, and I'm not going to discuss that. Okay. So that's why, strictly speaking, we need to do this estimate first, which is the logarithmic estimate for the Hilbert transform, because strictly speaking, I didn't show you that under which conditions on F, this integral is really finite, because in principle it can be infinite. Then this is vacuous because we are subtracting infinity from infinity, right? So strictly speaking, this estimate should have been first. So here is the bound at infinity, and actually C0 is bounded by some constant f in at infinity plus 1 over alpha log of something, f of at infinity 1 plus alpha, f homogeneous C alpha, f L1 to power alpha. So I like this estimate. This is not usually written in textbooks, but I like this estimate because this quantity inside is not only homogeneous in the order of f, but this is homogeneous under rescaling of x, if you count the dimensions, for instance. So that should be the correct estimate. Yes? L1 norm, let's assume it's finite, because that's what we use here. If f does not decay at all, this is not defined, unfortunately. I think this is the only correct estimate if you assume LP decay. Okay, so idea is very simple. Now we just want to estimate Hilbert transform at some fixed point x. Okay, so it must be simpler, and it is simpler. Here is our point x. We are going to divide the real line into 3 regions. The local region close to x, where kernel is singular. Here we have to use continuity. There is no other option. Okay. And there is intermediate region. Say 2, where we are just going to use that f is bounded. Okay. And then there is final region, where we have to use that f is decaying. So here we can use L1. That's it, actually. You can replace it with any LP, P finite. Yes. Yes. Yes, exactly. But you need something. And if you don't add something, you cannot make this expression dimensionally correct. Okay, so this is actually very straightforward. So let's say this is A, some length. And let's say this is R, another length. Okay? We are going to optimize them later. Okay? So we estimate, okay, this integral, forget about 1 over pi. In this region, when we estimate in this region, we introduce f of x. It's okay to introduce this only in I because it's symmetric around x. Okay? And then you do the brute force bound, exactly the same one as before. What do you get? You get some constant depending on alpha, this distance to power alpha, and semi-null. Okay? This is exactly the same estimate as before. Now you have this region, second region, where the distance ranges from A to R. What do? You don't need to introduce it here because we are already away from singularity, and you just estimate brute force. Using that, F is bounded. You pull this F out by its maximum, and you integrate this guy in this interval. What do you get? You get exactly log, because that's the antiderivative of the kernel, log of R over A times the maximum. Okay. Very good. This region is even easier. We don't do anything, basically. In this region, the observation is that now this is less than 1 over R. Pointwise, if Y is in this region, this is less than 1 over R. Then what remains? If you pull this out by 1 over R, you have integral of F. Okay. So what's the conclusion? The conclusion is that for any A and R, under the assumption that this is greater than A, this maximum is bounded by sum of these three. Now you pick A and R. Okay? So again, the maximum is bounded by sum of these three for any A and R. You just now pick A and R, and then you get this estimate. Okay, any questions? So the point is that with these key estimates, the C alpha boundedness and the logarithmic estimate, in principle, we can complete the proof of this result. Yes. So it needs to be actually explained better. It means that assume that there exists some T star such that for any capital T less than T star, we have a solution. The question is whether can we have solution after T star. Okay? The statement is that it is impossible if and only if this at infinity becomes infinite. Okay? Any questions? So now we go directly to singularity formation. So for this equation, the Gregorio model, you can basically ask the exact same question, whether these CK alpha solutions we construct actually show this behavior or not. Okay. So let me start directly to save time, directly by the self-similar ansatz and the profile equation. This is to save time. So one way, maybe the most direct way to test whether a PDE becomes singular in time or not is to look for self-similar singularity. Okay? So self-similar singularity. What does it mean? It means look for solutions of the form 1 over t star minus t to power b times some function, capital omega, which we will call the profile of singularity, at x over t star minus t to another power lambda. So this ansatz can be generalized, but let's just keep it simple like this. Okay. And here, the unknowns are basically this profile function, which is, of course, the most important thing, profile of singularity. But we also have these parameters, the scaling parameters. And of course, we also have T star. But we will see very soon, T star is not relevant simply because the equation is translation invariant in time. So T star doesn't play any role. We will see very soon. We will also see very soon that B has to be 1. We will see it. But I can explain it already simply because the equation is quadratic. Okay? Equation is quadratic, so if you take a time derivative of omega, that is supposed to balance with quadratic form in omega. So if you do some counting of powers in t, you see that b has to be 1, and I will show it soon. So if equation was cubic, for instance, b has to be 2, and so on. Okay. And again, you can try to put fancier ansatz. For example, this can be arbitrary function of t, and also for that, it turns out that it reduces to this form, except for very special case where it can be exponential in time, and that would give decaying solutions, self-similar decaying solutions. But that's not what we want anyways. So what does it mean precisely? Look for solutions of this form. It simply means that you plug this ansatz into the PDE, okay? Derive the equation for the profile and try to find the solution to that profile equation. Okay? So plug in the ansatz to, in our case, D Gregorio, and get the profile equation. So here is a quick remark. To do this, of course, we need to be able to calculate the Zygmund transform and the Hilbert transform of this expression. But we know how to do it because last time we checked that Hilbert transform is order 0 operator, which by definition says that if you apply the Hilbert transform to this rescaled guy, that is exactly the Hilbert transform of unrescaled guy evaluated at the rescaled point. So I will write this in formulas. So Hilbert of omega is, so Hilbert is linear transform. So this just goes out. And Hilbert of omega, whatever it is, and evaluated at this point. This is the computation that we did in the last part. And now let's give a name to this rescaled variable. We will call this maybe C. And as a general rule, the profile equation is defined in terms of the rescaled variable, not the original. Okay. And now, of course, we want to say that the Zygmund inverse of omega is Zygmund inverse of capital omega. We will use that, but for that, we need this zero integral condition. Okay. We don't need this for existence, uniqueness, and so forth. But just for this profile computation, we need this condition. But you don't need to worry about it. Okay, so let's actually plug this in to the equation. So actually the most challenging part, at least for me, is to compute time derivative because time derivative was here and here. And you are calculating time derivatives with very complicated chain rule, which I make mistakes all the time. I have done it at least 100 times in my life, but still it's a bit tricky. So what is the time derivative? Okay, so time derivative first here, that gives you b times t star minus t, b plus 1 times omega, of course. And you can ask why not minus b and b. Trust me, it's b. And then time derivative falls here. But now it's a very complicated chain rule. Okay, let's do this. T star minus t power b. And first of all, you have omega prime. This prime is with respect to this variable, c. So let me just write directly c. And you differentiate this in time. Then you get x over t star minus t to power lambda plus 1 with lambda. Okay? And this, you realize that we can factor out this power, basically. Okay? If we do that, we get exactly b omega plus lambda xc omega prime xc. Because this is exactly xc and another power of 1 over t star minus t, which combines with this, and then we pull that out. So it's exactly that. Now, these two terms are easy because we know basically that Hilbert's transform is an order 0 operator. So I skip the computation. And I will move this term to the right-hand side. What do we get? We get now, because the right-hand side is quadratic, we have this to power 2b times omega, Hilbert omega, minus omega prime, and Zygmunt inverse of omega. Okay. So what's going on in this term? Derivative is order 1 operator. The Zygmunt transform is order -1 operator. So in the end, we get the exact same factor. Now you see, these expressions in brackets are now independent of t in the c variable. But you have these factors of t hanging in front, and unless they are equal, we are not going to get any non-trivial solutions. So they have to cancel, which gives or which forces that b is 1. Okay. And then we obtain what is called b is 1, what is called the profile equation for the Gregorio equation. So here is, of course, the very important question: how do we solve this profile equation? So the quick answer is that it's not easy. It's not easy. And I will first state it as a theorem. So this was proved by myself and Tarek El-Gindi many years ago. The statement is that there exist solutions to the profile equation for C alpha with alpha sufficiently small. Okay. For any alpha sufficiently small, there exists a solution which belongs to C alpha. And some LP depending on alpha. It does not decay too fast, unfortunately. So as a direct corollary, we have solutions to the Gregorio, but only C alpha in space, which becomes infinite in finite time, T star. But you see, in the profile equation, T star does not enter. What does it mean? By choosing initial data appropriately, the solution can blow up at any T star we want. Because what do we do? You first pick T star and plug in T equals 0, and you choose that your initial data, omega 0. That is C alpha and also LP. So in the remaining time, I'm going to show you how we prove this result. And important point is why we need this condition. And in the last lecture, I will show you this remarkable analysis of Tarek, where he basically reduces 3D vorticity equation under axis symmetry into a form where it, in some sense, contains the de Gregorio model. And again, you need the condition that alpha is small. Alpha is regularity. Yes? So this, I don't remember the exact expression. It is some exponent, which is finite, but goes to infinity as alpha goes to 0. Sorry? Maybe, but I can say it behaves like 1 over alpha. I don't remember exactly. So you can basically derive the profile equation for any nonlinear evolution PDE that you like. For instance, the Navier-Stokes, the millennium problem, right? And then you get the profile equation. So somehow, if you can find the solution to the Navier-Stokes profile equation, you get the $1 million prize. And of course, no one succeeded so far. So what's the point? The profile equations in general are notoriously difficult to solve. They do not have any nice structure in general that we can use. So there are just basically a few cases where we can find the solution. We either find by luck, okay, by intense supercomputer simulation, or by some perturbation analysis from a solution that we already know of a different equation. And this result is of the last type. And what is the approximation that we are going to do? That is what is called the profile for the Konstantin-Lax-Maeda equation. So here is the idea. We drop this term completely. We drop this term. And that is the profile equation for the so-called Konstantin-Lax-Maeda equation. That is explicitly solvable. So we get all the solutions we want. But we are interested in this equation, not that equation. And we have removed this term, okay? And the point is that we hope that there are certain solutions of this equation for which this term is actually very small and hence approximates the solution to this equation. That's exactly where we need alpha small, and that's how we proved this theorem. So now I will write things down. So consider formally for now, maybe I will put the bars to avoid confusion. Omega bar plus lambda this equation. This is profile equation for the so-called Konstantin-Lax-Maeda model. Okay. Which was known to blow up in finite time using explicit formula, but it was observed only by Tarek Elgindi that singularity for this model is self-similar. And then we used this observation here. So this is solvable. It's solvable in the sense that for any alpha, we have a solution to this equation, which is C alpha. Okay? So for any alpha between 0 and 1, you can actually go up to 2, but let's not discuss it. Exists a solution depending on alpha, which is only C alpha and LP. Okay, next step, very naively, find a solution to the de Gregorio profile equation, which is alpha close to this guy. Find solution to this de Gregorio profile equation, call it star, which is close to this CLM profiles. And here we need alpha small. And then later, people even did numerical simulations on this, how small alpha needs to be for this to work. Some people, some Italians, I think, found that you can actually go up to alpha equals 0.7, something like that. Please don't quote me for this number, but in our theorem, it needs to be very small. Okay, any questions so far?
If the scout alpha is large, right, you may not get very well infinity, but two are very nice.
That's a great point. Yeah, I understand what you are saying, but it's different. So this is from the behavior of this guy, and Anna, I agree that for smooth blow-ups, that is usually the general rule. But I think they are just in different world. In the smooth category, yes, you are absolutely right. Yes, you are absolutely right.
These equations are non-local in nature. So even if you have go up at certain state, how do you make sure that far away things are not destroying you? Equations are non-local, right?
Yes, yes.
So you have go up at certain state. So, but are you making sure that far away things are not destroying your block phenomenon? Interactions can be also with far away.
Sure. For general solutions, absolutely, you are right. But at least for these exactly self-similar solutions, or maybe I should have drawn a picture. That does not happen, at least for this exact solution. So I should have drawn you a picture. So this profile looks like this. And for alpha small, you have C alpha cusp here. So it has some peak, and then monotonically decreases to 0. That's why it's okay, basically, for this particular profiles. And if you take t closer to the singularity time, the behavior is just focusing. And then it becomes infinity, in at infinity, which is absolutely necessary for blow-up. Okay. Yes, strictly speaking, you are right. If you take any function omega, okay, if there is a solution of this form, it doesn't mean that there is singularity formation. There are some conditions on omega that you need for this to be actually singularity. Okay, so in the remaining time, I will just speed up and discuss some technical details. Oh, but of course, I have to explain the heuristics. Why smallness of this term requires small alpha, and what is the physical reasoning behind? Actually, all of this started with a very long, well-known observation that in the 3D fluid equations, Euler and also Navier-Stokes, the transport term somehow always tries to destroy singularity formation. And this has been observed in many numerical works. So in the Konstantin-Laxmaeda model, you just remove the transport, and somehow it blows up very easily. For any data, basically, it blows up. There's even explicit formula. But again, in the de Gregorio, what happens if you do numerical simulation is that while this term tries to increase the maximum of omega, the transport tries to undo it. And you can see it from this kind of geometry. Okay? If you have a solution like this, the point of having a solution like this is that the Hilbert transform of such a solution has maximum at the origin and decays monotonically from the origin. So near the origin, you have large amplification of omega, and it decays afterwards. So if you only have the right-hand side, what happens to this solution is what you want. It amplifies only near the origin. But then what does the transport do? Velocity is antiderivative of the Hilbert transform. Okay? And because the Hilbert transform was positive near the origin, which is necessary to get blow up, this is positive for x positive. So the transport is somehow always pushing you away from the point where you want blow up. It's always the case, even in 3D vorticity equation. Okay, you see, the derivative had to be positive to get blow up in the first place, but velocity is antiderivative of positive. So it's positive. It pushes the solution away from the singularity. And here comes the very important observation. These two terms, in terms of scaling, they are of the same order. But the point is that if, so this is just heuristics, if the profile omega, profile for CRM or de Gregorio doesn't matter, near the origin is only C alpha exactly and not better, there is smallness coming from the transport, because it may look very stupid, but that's what it is. If you take the derivative, you get alpha. Actually, that's it. If you have a x to alpha function, if you differentiate, you get alpha. Intuitively, what's going on? This is in terms of the formula. Intuitively, what's going on? Assume in the extreme case where alpha is 0, then we want odd symmetry to make the Hilbert transform large at the origin. intuitively, it means we just have a step function. Okay? But what does this transport do to this, maybe it's called Heaviside function? What does transport do to this Heaviside function? Nothing. Absolutely nothing. So if you slightly regularize the Heaviside in a way that it is C alpha, now transport is order alpha. That's it. So formally, in the class of functions behaving like this near the origin, the Grigoriev model, not just the profile equation, the full model reduces, in some sense, to the CLM. But all the question now is about making precise this sense that one model approximates the other. So we develop a function framework, basically, to do this. Okay? So in the remaining time, I will just do the analysis. Yes? So first step, solving this CLM profile equation. So this relies on interesting formula for the trichomy identity. Unfortunately, and embarrassingly, I do not memorize the formula by heart. The formula gives the Hilbert transform of expressions of this form. Hilbert transform of f times Hilbert of f is minus 1/2 f squared minus Hilbert transform squared. This is called the trichomy identity. And solving this equation really relies on this identity. How do you prove it? You cannot avoid using the defect that in the upper complex plane, so by definition, it means the upper part of the complex plane, right, C plus, okay? If you have a complex analytic function in C plus, okay, which extends to a reasonable function on the boundary of C plus, okay, its imaginary part is the Hilbert transform of the real part, okay? So f is some complex analytic function in C plus, okay? Then the statement is that the Hilbert transform of real part of f restricted to the boundary. Let me just identify the boundary with our real line, is the imaginary part. So how do you prove this theorem? You have reasonable functions, f and hf. You consider, say, capital F, f plus ihf. And there is a way, for instance, using the Fourier transform to lift this function as a complex analytic function in C plus. Okay? That means f squared is also complex analytic in C++. And you just compute what F squared is. So what do you get? You get that Hilbert transform of F squared minus HF squared is 2 FHF. Another thing you can get from this theorem is that if you apply Hilbert transform twice, you get minus identity for any F. So you just apply H again, and you get this formula. Yes. But F doesn't need to be a continuous function. I think L1 log is enough. So I'm sorry, I do not want to spend much time. I will just show you immediately how we solve this equation using this identity. So what do? We define the complex analytic dependent variable. So we are solving the profile equation for CLM. And what do? We introduce, there is issue with notation. Let's say F is the complex analytic function whose trace on the boundary equals omega bar plus I times Hilbert omega bar. Okay. And what you can do is you can take the Hilbert transform of this equation. Here is some operator you need to deal with, but that goes through basically. So I will just go straight to the point. The point is that F, this complex analytic function, satisfies F plus lambda xc, F prime xc, equals, the right-hand side is the key, minus I over 2 F squared. Using the trichotomy identity. And then this is called Bernoulli ODE. And it was well known, somehow the solution was well known. What's the solution? So from this line to this, there's a lot of computations skipped. And it's not so easy. For instance, I cannot do it. I think you can derive that. So this is a first order ODE. It's a singular ODE, but you can still find solutions. It's first order, and there's one free parameter, C. And with that free parameter, this is the solution explicitly. It's 1 over some free constant times C to power 1 over lambda minus I over 2. But this has to be complex analytic in C++. That gives a restriction that the lambda is in some range. I'm sorry, it's not written in my notes. Sorry, it's not written in my notes. Yes. So 1 over lambda cannot be too large, basically, because then this has poles in C++. Okay? 1 over lambda needs to be small. I think the condition is like this. Okay? So if you want this profile. So we have already found the profile for CLM. You just take the real part, and that's the profile for CLM. But for this expression to make sense, we need this condition for analyticity. And furthermore, if you want this to be smooth, okay, if you are interested in smooth profiles, there's only one option for smooth, for F to be smooth. So this smooth profile gives blow up for CLM for smooth data, but that profile, you cannot continue it to de Gregorio, at least numerically. Okay. But what's the point here? The point here is that now we have C alpha profiles, which are by definition omega bar with alpha is the real part of C is irrelevant. You can take any non-zero C, maybe positive, alpha minus I over 2. So what's the point? We take lambda to be 1 over alpha. Okay. This is complex analytic in the upper complex plane. Good. Now, first step is done. Of course, all the hard work is in the second step. We now want to come back to this profile equation for de Gregorio and find a solution to this near that explicit function. All the key observation is that if you calculate this for that explicit function, that is actually alpha smaller than this. But the question is exactly in which function spaces. Okay, so now let's go to the second part. So here is what you imagine. Imagine that want to find solution, the form of this equation, which is omega bar alpha, this is explicit, plus small perturbation, which is hopefully of size alpha. Okay, say omega 1. For alpha small. And let's derive the equation for omega 1. I derived it this morning. Then, so this is solution ansatz for our actual equation. Then omega 1 plus, after dividing by alpha, 1 over alpha C omega 1 times C. I will write some terms in the left-hand side. Omega bar alpha, Hilbert omega 1 minus omega 1, Hilbert omega bar alpha. This is also explicit. This is the imaginary part of that f function, equals minus Sigmund inverse of the CLM profile times the derivative. plus terms of order alpha. I didn't skip any terms in this computation. We are actually almost done. So if you see the left-hand side, if you look carefully, it takes the form of a linear operator applied to omega 1. And the right-hand side is some given function, explicit. What is the linear operator here? The linear operator, say f for simplicity, is by definition f plus 1 over alpha c f prime. Yeah, maybe I didn't have to really write it down. Sorry. F. This linear operator can be inverted using the same trick and solving a Bernoulli ODE again. The linear operator can be inverted up to one consistency condition. That consistency condition comes from the fact that when we solve the Bernoulli ODE, we work under the assumption that our function f that we want to find, we want to solve for this f with given right-hand side. This function is supposed to be the trace, the real part of trace of a complex analytic function on C+. That gives a consistency condition on the right-hand side. But the right-hand side is given. We have nothing to do. So can we solve it? The answer is no. We cannot solve it. There is another question you should ask. This term is order 1 over alpha. Why is it there? It's because it's coming exactly from the same observation that this is transport in the C variable. So this term should be order alpha, so that this is actually order 1. So we make it completely explicit with another change of variables. Now we put tildes and introduce a new independent variable, which is just, by definition, original function evaluated at this. And this is consistent with our expectation, which was never used so far, that omega 1 in the original coordinate should be like this. So in principle, if you introduce the new variable like this, w, this tilde function can be smooth in w. And that's what we do. We are going to solve this equation in the w coordinates in the class of very smooth functions. What's the point? If you introduce this w, everything changes to tildes, although you get now a distorted Hilbert transform, H tilde, depending on alpha, okay? But the key observation here is that you differentiate this in W. Omega tilde prime is 1 over alpha, omega 1 prime. So that if you multiply back by W, you get exactly this, and you see 1 over alpha. So in the W variable, this is exactly W. But the problem is that you get a distorted Hilbert transform, which now you have to develop the whole theory of boundedness and so on. That's okay. You can eventually do it. But now the same problem remains. This operator, even in W coordinates, it's just a change of coordinates, requires a solvability condition on the right-hand side. So the observation, important observation, which was well known in the dispersive community, is that you have to perturb lambda also. If you insist on having the same lambda, there's simply no solution. But there is no reason why lambda has to be exactly 1 over alpha for the Gregorian, and it's not. So what does it mean? We are looking for solutions not exactly 1 over alpha, but with some perturbation, which is order 1. So very important point of solving this profile equation is that lambda, the scaling exponent, has the exact same status as the profile. It's a mysterious unknown, which you do not know in advance. They have the same status, exactly the same. So now, if you introduce lambda 1, which is another unknown, you get additional term on the right-hand side, which I computed. And that is exactly minus lambda 1 in the new coordinate, W omega bar alpha prime plus small terms. And this is now free. So here is the idea. I will just finish by saying only the ideas. By introducing an additional unknown, we can find lambda 1 such that the right-hand side now is in the image of this linear operator, which we have explicit formula for the inverse. So omega 1 tilde now is defined by the inverse of the right-hand side, but there is a kernel. The operator is Fredholm of index 0. Image is codimension 1, so it has kernel. So you need to make a choice. There's a unique choice, basically, which makes this function very smooth. It's a smoothness condition, basically. So you define omega 1 tilde. That's basically the story. An important technical part is, let's say this is the right-hand side. And there is functional analysis question. We want to do this fixed point argument in some Banach space, okay? And what we need is that for our function f in some Banach space, this expression should be bounded in the same Banach space. And intuitively it's okay, and we prove that it's okay. The right-hand side loses one derivative. It's here, basically. The right-hand side loses one derivative, but this inverse gains one derivative. So we can find a Banach space for which this scheme defines an operator for which we can apply the fixed point theory. And in tomorrow's talk, maybe we will see situations where this cannot be bounded. but that's not the end of the world. But for this model, you can just use a fixed point method. Okay, that's it. Thank you. 2D? That's a good question. You can remove this term and say there is a model for 2D Euler. Maybe, yes. But people didn't really study this model so far. There is global existence and uniqueness because omega is finite. I personally think this can be a very interesting equation to study. For instance, the long time limit. I think no one really studied this model. Yes?
Lambda 1. Can you see the profile for with alpha replaced by 1 by alpha plus, sorry, lambda replaced by 1 by alpha plus lambda?
Ah,
So why this extra, like, this alpha is the profile for alpha?
yes, that's a good question. We first fix some alpha, okay? Then we have that profile, okay? And what we want to do, we want to find solution to this equation whose behavior near zero is like this. Okay? The claim, if you insist on having lambda equal to 1 over alpha, there's no solution. You need to perturb it. Then there is a solution. You first fix alpha, and you only consider functions which behave like this. Then, somehow, lambda must be perturbed as well. Otherwise, simply there is no solution. Sorry? Oh, because that's a very good question. Because our equation is lambda, and you compare the equation solved by the profile. The profile satisfies omega bar alpha plus 1 over alpha c omega bar alpha c prime and some right-hand side. So there is now some disparity. If lambda is not exactly 1 over alpha, that disparity subtracts to the right-hand side. And this is what people call the modulation parameter to force the right-hand side to be in the range of the linearized operator. This is kind of standard scheme now. Yes, thank you very much for the question. Yes?
So the equation is non-linear, but then you end up with a linear operator. Where was the where did the non-linearity end?
All the non-linearity is in the right-hand side now.
So shouldn't you have also non-linearity in omega 1?
Yes, that I hide in the, because equation is quadratic, it's smaller term. Of course, in the analysis, you cannot neglect them. Big O of alpha, you are right.
Does that term be small or the alpha squared, right?
It's alpha squared originally, but I divided everything by alpha.
Okay.
Yes.
So
Yeah.
for the one that becomes for the alpha.
Exactly. Thank you very much for the question. Yes. I hide everything in the right-hand side.
Hey, so let's take a break, then we come back.
Okay, great. Thank you.